Okay, hello. This is the second quiz walkthrough guide video on conditional probability. So, uh, I'm going to walk you through all the algebraic questions, but I found that there are only basically two types of questions. One is to calculate a conditional probability, and the other is to use the Bayes rule or flipping the conditional probability. So actually the same pattern is repeated again and again. Still, I'm going to show you all the questions, but maybe you may just skip like some questions and try just them by yourself if you think you can try them by yourself. So I believe you will catch the basic idea if you repeatedly trying the questions. Okay, the first one, the simplest possible conditional probability, rolling a dice. So when you roll a dice, find the conditional probability of 4 or greater outcome, given that the outcome is odd. So it is simple, but let's imagine. Let's see. Let me explain what it means. So it's like this. When you throw a dice, if the outcome is odd, then you record the outcome as data. But if your outcome is even, then you don't record that, or just delete that record. So you only choose odd numbers after rolling a dice, and then calculate, then check the proportion of outcomes being 4 or greater, right? So pretty simple. The idea is like this. So the conditioning event we only consider is a set of odd numbers, which is obvious. 1, 3, 4. There are only 3 possible outcomes under given this condition, right? Now it's rolling like a dice with 3 faces. So there is no other numbers on the dice you can imagine, like in this conditioning event. And then among these 3 outcomes, only one of them is 4 or greater, right? So the main event is 4 or greater. That happens once out of 1 out of 3. And we know each of them are equally likely. So the probability is 1 over 3. That's it. So, okay, simple. And second question. A ride-sharing and food delivery company has collected the data on usage of the service. So find the conditional probability that a customer uses ride-sharing service given that the customer uses food delivery, right? So we have food delivery service. So the first row are the customers who have used food delivery service. So we are going to delete the second row. So under our condition, we only need the first row, 240 plus 360. Out of this much, we are calculating the probability of ride-sharing service. So only 240 out of these two use ride-sharing. This is the conditional probability. Okay, so pretty straightforward. And by the way, I should have told you this. Your numbers may be different in your question, so it's randomized. So the events I'm asking you may be different. So be a little more careful. But if you happen to have the same question, same numbers, this is how you calculate the probability. Okay. Another similar question. Some words have particularly high probabilities of occurring in spam emails. So for example, Viagra is frequently seen in spam emails, but rarely used in non-spam emails. So the Bayesian spam filtering is an email filtering system based on this idea. So like for example, if you detect a word, say Viagra, then treat it treat those emails as spam, right? So of course there are more like if like the condition, there are more words, more kind of like alert words, and if there are a certain number of alerts, then the email is considered as spam, like filtered as spam, something like that. So to implement this, the conditional probability of a spam email for each word has to be calculated first. So given a word, like for example, Viagra, what is the probability of being a spam email if the email contains this word? For example, for another example, statistics, for example. So if an email contains a word statistics, how likely it is a spam email? I don't know. But so like for different words, those probabilities will be different. So that's basically a conditional probability. Okay? So then to calculate that conditional probability, a random sample of 1,000 emails are collected and reviewed. If those emails contain this email contains a certain word, say statistics, and if the email is spam. The results, so here, probability distribution table. So that means if the word is contained or not, and if the email is spam or not, right? 2 by 2. And then, which email has a higher chance of being a spam email, containing the word or not? So you are calculating, like comparing two conditional probabilities. So what we are going to do here is, what we are going to compare is, basically we are interested in the chance of being a spam mail. So the main event is being a spam email, the email being a spam. But we change the condition. The condition is whether the email contains a word, statistics, or not, right? So we will calculate two conditional probabilities, and it works like this. So if the word is contained, then the probability of spam email is calculated like this. So condition is containing the word, the first row, only use the first row observations, and out of this much, 5%, out of 5 plus 20%, 5% are spam emails. So the ratio is the conditional probability. On the other hand, if you change the condition to the emails that do not contain the word, then out of this much, like 15 plus 60%, out of that, 15% are spam emails. So the ratio, the conditional probability is 15% out of 65%, right? So you calculate those two conditional probabilities, and then you can tell which side is more likely to be a spam email, whether the word is contained or whether the word is not contained, right? So you can compare the numbers. As I said, the numbers may be different in your question, so you just get the idea and try by yourself. Next question. Another question in the same framework. An online computer store conducted a survey to its members whether they were planning to purchase a computer within a year. And 1 year later, the survey respondents' purchase records were reviewed. So first, I surveyed whether they are planning, and then 1 year later, I checked actually they purchased or not, right? So, and here is the frequency distribution table. First, by rows, we have whether a customer, a member, planned or not, right? Planned to purchase a new computer or not. And then we actually observe the results. Actually purchase the computer or purchase only parts and or did nothing. So we observe three categories. But like it's 2 by 3, but not much different. Um, we are going to check if those events are independent or not. Like, so as a retailer, I was wondering if planning actually leads to real purchase or not. If yes, maybe we can give some, discounts to those who planned. But if they are independent, it's kind of purchasing is random. So maybe the marketing strategy could be different if depending on the independence. Okay. So here, I'm going to show you how to check the first independence. So I'm going to check the independence between plan to purchase with independence between this and purchasing a computer, right? These two events, right? I'm going to show you how to check the independence, and then you can apply the same idea to the other pair. The other pair is planned and purchase parts. So you can just apply the same method to check the other independence. So for the first pair of events, there are like two different methods to check the independence. But first method I'm going to show you both methods here. But first method is to compare the probability of actually purchasing a computer and unconditionally versus conditional on the customer planned to purchase a computer, right? So if this equality holds, then two events are independent, right? I believe you remember what it means. Conditioning on plan or not, actually the probability of purchasing a computer does not change. That means they are independent. Okay, so I will calculate those two probabilities and then checking if they are equal. It's easy. First, unconditional probability. Unconditional probability of purchasing a computer is out of the total number, sum out all the numbers, all the observations. Out of the total observation sample size, numerator includes these two types, right? Only 60 plus 120 customers purchased the computer, right? That's in the numerator. That's unconditional probability. It is unconditional because we use the denominator includes all the observations without restricting them with a condition, right? But a conditional probability restricts the sample. So restrict the sample to those who planned. So planned to purchase. So delete the second row. And we only use the first row that is in the denominator. And among the first row, observations in the first row, only 60 customers purchased a computer. So 60 on top. Now it's your job. Your job is to calculate those two probabilities and see if they are equal. If they are equal, these two events are independent. Okay, this is method 1. Actually, you may change the role of plan and purchase when you calculate the conditional probability. Switch their roles using purchase as a condition and planning as the main event. It is also possible. Basically, idea is the same. We are going to calculate unconditional probability of planning to purchase. That is out of all observations. So denominator includes all numbers. Out of them, this 3 categories, 3 types planned to purchase a computer. So this much goes to the numerator. Okay? So numerator includes the sum of three numbers. So that is unconditional probability of planning to purchase a computer. But compare this with a conditional probability of planning to purchase a computer among those who actually purchase the computer. So among the actual buyers, how many planned to buy a computer? So then now we restrict our sample to those who purchased a computer. So this part, the first column, is the only observations that satisfy the condition. So the denominator is these two numbers, and numerator is those who planned, right? 60 out of 60 plus 120. Again, you can compare them and see if they are equal. So if you did method 1 and the previous method 1, and then this method, if you do it again with this way, the conclusion should be the same. Otherwise, if for example, if you get the same numbers here, but those numbers are different, then something is wrong. So you can double check your answer by trying different methods and see if they imply the same conclusion. They must imply the same conclusion, otherwise maybe a mistake. By the way, there is another method, method 2, which is based on the special multiplication rule. So in here, you have to calculate 3 unconditional probabilities. So first, probability of intersection, and then probability of planning, probability of purchase, right? All unconditional. So all the 3 probabilities have the same denominator, the whole sample, and numerator changes. First, intersection. So those who planned and actually purchased, only one type, that is 60. And the second probability, those who planned, that include 3 types, right? So this much numerator. And finally, the third probability, unconditional probability of purchasing a computer. That's these 2 types. So first column, that comes to here. Now, you have to calculate 3 probabilities, and then you multiply the latter 2 probabilities and see if the product equals the intersection probability or not. If they are equal, those 2 events are independent. If not, they are not independent. Okay? So as I said, I gave you 3 possible methods. And all 3, it doesn't matter which one you use, but anyhow, all 3 methods must tell you the same thing. Otherwise, something is wrong. You made a mistake. So you can just check your algebra by cross-checking your algebra by trying different methods. And what I have just done is only about the first pair, right? You need to do the same thing for the second pair to check the independence between different pair of events. So that is your job. I believe it's purely just algebra, simple algebra. So I don't worry too much about that. Okay, so that's your exercise. Okay, next question. So far, all those questions up to here have been calculating conditional probabilities based on 2x2 table or joint distribution table or like frequencies. But now we are going to consider the Bayes rule. From now, the information is given as a conditional probability. So think about this question. A standard certification test was given at 2 locations. 40% took the test at location A and 60% at location B. The percentages of candidates from locations A and B who passed the test were 62% and 60%. So those who took the test at A so 62% of exam takers at A have passed the exam, and 60% at location B. And among those who passed the test, what is the conditional probability that the candidate took the test at location A? Here, I'm going to use, by the way, you may use the Bayes rule. It's not a, that's actually maybe easier, but I'm going to show you the tree method, like classification method. So this is what I recommend, but it is up to you. If you want to use the formula, then open the slide and apply the formula, and then you will get the same answer. Okay, so let me show you this method. I'm going to consider 1,000 exam takers, and out of 1,000, we already know that 40% take the test at location A, and the other 600 takers take the test at B. So I used unconditional probability to classify 1,000 exam takers. And among the 400 exam takers at location A, 62% have passed the exam. So this is a conditional probability. So conditional on the location A, right? And then if you calculate 62% of 400, it's exactly 248. So 248 exam takers pass the exam at location A. But the other 400 minus 248 failed at location A. Meanwhile, 600 exam takers at B, among them, only 60% passed the exam. And then 60% of 600 equals 360. This is the number of exam takers who passed the exam. And 600 minus 360 equals 240. This is the number of the takers who failed the exam and at location B. Okay, so we classified 1,000 exam takers into A and B by location, and then classify them again whether they pass or fail, fail, depending on the location, using conditional probabilities. Then in the end, we want to check the ratio of location A out of those who pass the test, right? Our condition is passing the test, so that's 248 plus 360. So this much passed at location A and this much passed at location B. And among them, 248 pass at location A. So this ratio is the conditional probability. Okay. So I'm going to repeat the same structure in the following questions. Two messenger services deliver to a small town. Service A has 30% of all the scheduled deliveries, and B has the other 70%. Their on-time rates are 80% and 60%. Calculate the probability that a package is delivered on time. I will do the same thing. 1,000 deliveries. Think about 1,000. And I know the portion of each delivery company's services. Service A delivers 300 packages, and Service B delivers 700 packages. And out of 300 packages delivered by A, 80% are delivered on time. So that would be 240 packages. Okay? Then automatically, the other 60 packages are late. Similarly, 700 packages delivered by B, the on-time rate is 60%. So 60% of 700 equals 420. 420 packages are delivered on time. And the other 280 packages are late. So we classified 1,000 packages into 4 types. So in the end, we would like to calculate the overall on-time delivery rate. That's like out of 1,000 packages, unconditional probability. So denominator is everything, 1,000. 240 plus 420 packages are delivered on time. So this is the on-time rate overall. Okay? So same structure as we did before. The next question, again, the same structure. I have noted from past experience that a student who has done all assignments has a probability of 90% of getting B- or better, while a student who has missed some assignments has a probability of 30% of getting B- of better, right? And I expect 75% of students will do all the assignments this semester, right? Based on those probabilities, what is the probability that a student gets B- or better this semester? Okay, we'll do the same thing. 1,000 students again. Suppose that 1,000 students take this course, and then I expect 75% of them are going to do all the quizzes, right? Try all the quizzes and use up the attempts. The maximum attempt is 10 times. So I expect 75% of students use all the attempts so to get the best outcome. That means out of 1,750 will do all quizzes, do all assignments, and the other 250 will miss something. Then out of 750 students who try all quizzes, 90% will get B- or better. 90% of 750 equals 675. So 675 students would get B- or better because they did all their assignments. On the other side, 250 students miss some quizzes, so as a result, only 30% can get B- or better. So 30% of 250, if you calculate that, it is 75 students. So only 75 students get B- or better after missing some assignments. And the other 175 will get a lower grade. And then, after all, what is the unconditional probability that a student gets B- or better? Out of 1,000 students, according to our classification, 675 plus 75 students get B- or better. So this is the unconditional probability. Okay. So another another question with the same structure, free throw question. So usually when like in basketball, usually 2 free throws are given to a shooting foul, and then I'll assume that the percentage of making the first free throw is 75%, and if the first one is made, then the probability of making the second one is higher, 85%. However, if the first one is failed, then the percentage of the second one is lower at 65%, right? So you get the idea. And then what is the probability of making both free throws? Interesting question. If you like basketball, it makes sense. Of course, the numbers may be different in reality. But let's try this. Now I'm going to choose 10,000 cases, right? 10,000 fouls, shooting fouls. I choose 10,000 because later I will show you the number. So if you choose, like say, for example, 1,000, then you are going to get a number like 637.5 free throws. So mathematically that's not a problem, but it does not make sense in our storytelling. So I'm going to use a larger number to avoid decimals, right? To keep the numbers, whole number to integers, I'm going to use 10,000. So anyhow, you observe 10,000 cases, and according to our assumption, 75% of them make the first free throw. So 7,500 cases make the first free throw, and the other 2,500 cases miss the first one. And now, like among the cases where the first throw is made, 85% also make the second one. So we need to calculate 85% of this number. So out of 7,500, the 85% equals this number, 6,375. This many times, also the second free throw is made. But 1,125 failed the second free throw after making the first one. Okay? So this is the cases when you make the first throw. On the other hand, 2,500 cases make the first throws, but only 65% makes the second one. Miss the. So 2,500 cases fail the first free throw, but 65% make the second one after failing the first one. So that is 1,625 make the second one after the failure of the first one. But 875 cases, both free throws are missed, right? And then as a result, what we are interested in is the probability of making both free throws unconditionally. So denominator is 10,000, and the event of making both free throws is only this type. So out of the 4 different types outcomes, we are calculating this probability. So it's easy, 63.75%. Okay, so that is how you calculate unconditional probability. And yeah, this is it. So as I said, I repeat the same practice again and again, because repetition is the best way to learn something, to understand something. So, and I want you to understand the idea. And once you understand the idea, you can speed up, and like you can use the formula. Maybe it will be more natural to use the formula when you understand that, and you can easily use the formula. So that's what I want. Okay. Anyhow, thank you for watching the video. If you have any more questions, please let me know. I'll be happy to help you. And chapter 3 will be uploaded soon. See you next week.